Solution of Laplace's equations in spherical coordinates by separation of variable method. We'll see how we use separation of variable method to solve Laplace's equations in spherical coordinate systems. Okay, so we have Laplace's equation is given by gradient square or Laplacian of V equal to 0, where V is some potential. Okay, where V is a function of r theta phi, as we do in spherical coordinate systems. In spherical coordinate systems, we have the formula 1 upon small r square delta upon delta r square delta v upon delta r plus 1 upon r square sine theta delta upon delta theta sine theta delta v upon delta theta plus 1 upon r square sine square theta delta square v upon delta phi square equal to 0. Remember, we have a portion equation is given by delta square V equal to charge density upon epsilon naught, wherein if we have any reason their charge is not present, then portion equation is changes to Laplace equation, which is given here delta square V equal to 0. We shall consider potential, which is azimuthal symmetry. Okay, so that V is independent of angle phi. If we have azimuthal symmetry, then phi will be constant and d phi will be 0. So now V is the potential is only dependent on small r and theta. So Laplace's equation is delta square V equal to 0. Now we have the form 1 upon r square delta upon delta r square delta v upon delta r plus 1 upon r square sine theta delta upon delta theta sine theta delta v upon delta theta equal to 0. So now if you can write the first term, that is 1 upon r square delta upon delta r square delta v upon delta r, as delta upon delta r square delta v upon delta r plus 1 upon sine theta delta upon delta theta of sine theta delta v upon delta theta equal to 0. Okay, so we have this formula, but here V is dependent on r and dependent on theta. So by separation of variable method, we will do one thing, that we will product two variables which is only dependent on, one is only dependent on small r and another is only dependent on theta. This is the same thing we used to do in derivation from time independent Schrodinger equation, from time dependent Schrodinger equations. Okay, so now V equal to V of r theta, which is equal to capital R, which is a function of small r, and capital theta, which is a function of small theta. Okay, this symbol is capital theta. So we'll put this in above equations. So delta upon delta r of r square delta of capital R capital theta upon delta r plus 1 upon sine theta delta upon delta theta of sine theta delta r theta upon delta small theta equal to 0. So the first term here, there is a derivative with respect to r, special partial derivative, and capital theta is constant there. So taking capital theta outside from the derivative sign, so capital theta delta upon delta r square delta capital R upon delta r plus capital R upon sine theta delta upon delta theta into sine theta delta capital theta upon delta theta equal to 0. So both equations, so these two terms are divided by capital R capital theta. So we got 1 upon capital R delta upon delta r. So r square delta capital R upon delta r plus 1 upon capital theta sine theta delta upon delta theta sine theta delta capital theta upon delta theta equal to 0. Okay, so the term in the blue, 1 upon capital R delta upon delta r square delta r upon delta r, is only dependent upon the small r term. Okay, and the red one, 1 upon capital theta sine theta delta upon delta theta sine theta delta theta upon delta theta, is only dependent upon the theta. So each part is a constant, because you can see check the dimension here. Okay, so each part is constant. So taking same as the constant any C, capital C. Okay, so you can see capital C plus negative capital C equal to 0. So we equate these terms into capital C because they are dimensionless. Okay, so we will equate C equal to L into L plus 1. You will see why this is convenient. Okay, so I equate 1 upon capital R delta R upon delta this term into L into L plus 1, another is which is negative C is written as negative R multiplied by L plus 1. Okay, so we will solution both these equations separately. The first one is answer is capital R, which is a function of small r, equal to a r to the power L plus b upon r to the power L plus 1. Here a and b is any constant. Okay, then now this one is delta upon delta theta sin theta delta capital theta upon delta theta equal to negative L into L plus 1 sin theta into capital theta. So we will shift the capital theta sin theta terms into right hand sides. Okay, the only acceptable solution here is when L is an integer. That is why we took this fancy from this constant. The solution are Legendre polynomials in the variable cos theta. I shall discuss Legendre polynomial soon. Okay, so you can see the Legendre polynomial that we have in Cartesian coordinate system. If we change that one to spherical coordinate system, it will look like this one. Okay, so the solution here is the capital theta, which is a function of theta, equal to C PL cos theta. PL is a Legendre polynomial. Okay, so this is the independent solution of R term and theta term. We defined before that V of R theta equal to capital R multiplied by capital theta. So we just put the solution here. So V of R theta equal to A R to the power L plus B R to the upon R to the power L plus 1 PL cos theta. You can see where is C. Okay, the capital theta equal to C PL cos theta, right? So if we multiply it as C into A and C into B, this will be a constant. Okay, so we don't much care about that. So it's just a constant. So there is no need to include the constant C. Okay, here because it is observed into A and B. So this is the required solutions. So separation of variables in infinite set of solution, one for each L. So the general solution is a combination of solutions. So we can write in terms of like a summation series. So L equal to 0 to infinity, A L lower index L R higher index L plus B L upon R to the power L plus 1 PL cos theta. Okay, so by azimuthal symmetry where theta equal where phi is constant, so d phi equal to 0, so V was V equal to R theta and delta square V equal to 0 is a Laplacian equations. So we have the form here 1 upon capital R delta upon delta R square delta R upon delta R plus 1 upon capital theta sin theta delta upon delta theta sin theta delta capital theta upon delta theta equal to 0. Here the required solution that we have here, B equal to R theta equal to L equal to 0 to infinity summation AL RL plus BL upon R to the power L plus 1 PL cos theta. So just to discuss some about Legendre polynomial. We will discuss briefly here, but in another video we will discuss much and great details about Legendre polynomials and special function like Laguerre, Hermite and Bessel functions. Okay, so these are this solution of differential equations of 1 minus x square d square y upon dx square negative 2x dy upon dx plus L into L plus 1 y equal to 0. So this was the real Legendre differential equation where L is 0 to up to 1 to 3 so on and so forth, integers. Well, this is the typical values of PLX where L is 0, 1, 2, 3. So P0x is equal to 1. You can see in the green line, this is just a 1, just a straight line parallel to x-axis. And P1 equal to x, which is y equal to x graph. P2x equal to 3x square minus 1 upon 2. P3x equal to 5x cube minus 3x upon 2. But you should remember one thing here, the range and domain of the Legendre polynomial is both negative 1 to 1. Okay, so here PL of 1 equal to 1 for all L because P 0 1. Okay, so PL of negative 1 equal to negative 1 to the power L for all L. Okay, so we can produce any of PL by using Rodriguez formula. PL equal to 1 upon 2 to the power L factorial dl upon dxl of x square minus 1 to the power L. dl upon dxl time means L times derivative of x square minus 1 to the power L. So let's calculate P3. for some instance P3 equal to 1 upon well, P3 is like L equal to 3, so put L equal to 3 here. P3 equal to 1 upon 2 to the power 3 factorial dq upon dxq, third times derivative of x square minus 1 to the power 3. So we just first calculate x square. What is x square minus 1 to power q, right? So x square minus 1 to the power q will be x square minus 1 multiplied by x square minus 1 plus square. Okay, so x square minus 1 plus square equal to x fourth of minus 2x plus 1. So this whole multiply is given by x6 negative 3x fourth plus 3x square minus 1. So this is the what we have, x square minus 1 to the power cube. So first derivative, this one, first derivative is 6x5 negative 12x cube plus 6x. Next one is next derivative is 30x fourth negative 36x square plus 6. So one more derivative is given by 120x cube negative 72x. So then calculate 1 upon 2 to the power cube, 3 factorial will be 3 factorial is 6, 2 to the power cube is 8, so 1 upon 48. So just multiply both one, so P3 will be 1 upon 48, 120x cube negative 72x. So just write in some function, P3 equal to 5 upon 2x cube negative 3 upon 2x, and P3 equal to 1 half 5x cube or x by 2, let's say common, so 5x square minus 3. So this is the required solution to P3. Okay, so similarly we can write P4, P5, P2, P1, anything. So Legendre polynomial are complete and orthogonal in the interval negative 1 to 1. So orthogonality conditions, so complete f of x equal to 0 to 0 to infinity Cj pi of x. So this is the orthogonality condition of these Legendre polynomials. So within negative 1 to 1, which is defined range of range and domain of the Legendre polynomial, well, Pnx and multiplied by Pm of x into dx equal to delta mn. You can say delta mn is a Kronecker delta function which is equal to 1 if m and n is same, and if they're different this will be 0. So delta mn into 2 of upon 2n plus 1. So in our work we are used to deal with a spherical coordinate system in this section. So put x equal to cos theta, so dx will be negative of sin theta. So for x equal to 1, theta will be 0 because for theta equal to cos 0 equal to 1. Okay, and x equal to negative 1 for theta equal to 5. So we'll changes the limit of integration from minus 1 to 1 to 0 to pi. So now the integration will be negative 1 to 1, Pn of x, Pm of x dx will be 0 to pi, Pn cos theta, sin theta d theta, which is equal to delta mn 2 upon 2n plus 1. This is the orthogonality condition in spherical coordinate system. Okay, so we have the formula here, b of r theta equal to al rl plus bl upon rl plus 1 into pl cos theta. So let's have a solution, let's have problem of electrostatics, where the potential v naught theta is specified on the surface of a hollow sphere. We have hollow sphere where the potential v0 theta is defined, which is of radius r. Find the potential inside the sphere. Okay, is asking to find the potential inside the sphere. So in this case BL equal to 0, we taken BL equal to 0 for all L, otherwise the potential would be low at the origin. Okay, so we don't have BL terms here, so just write V of r theta equal to summation of L equal to 0 to infinity AL r to the power L PL cos theta. Okay, so just equating small r equal to capital R, we have V naught theta equal to L equal to 0 to infinity AL r to the power small l PL cos theta. So now just multiplying Pm both the side. Why we multiplying Pm on the both sides? Because we have to using the orthogonality condition. That's why we are using it. So Pm multiplied by V naught theta equal to Pm AL r to the power L PL. So just multiplying Pm within the summation So we got Pm V naught theta equal to L equal to 0 to infinity Al r to the power L Pm into PL. Okay. So 0 to pi Pm V naught theta sin theta d theta equal to 0 to pi L equal to 0 to infinity Al r to the power L Pm into PL sin theta d theta. Just write like multiplying sin theta and derivative with respect to theta in the limit 0 to pi. Okay, we just did this one. So now Pm V naught theta sin theta equal to 0 to pi Al RL Pm PL sin theta d theta. So we have right hand side we have the orthogonality condition. Okay, so Pm PL sin theta d theta 0 to pi. So Al is taken common am. Okay, so it doesn't matter that where it's L or M, so just am taken calculate r to the power m. Okay, so 2 upon 2m plus 1. There was 2 upon 2n plus 1, right? The orthogonality conditions. So we have 2 upon 2m plus 1. So 0 to pi Pm V naught theta sin theta d theta equal to 2am r to the power m upon 2m plus 1. So am equal to 2m plus 1 upon 2r to the power m 0 to pi V naught theta Pm cos theta sin theta d theta. Okay, so m just equating m equal to L, we have Al equal to 2L plus 1 upon 2 r to the power L 0 to pi V naught theta PL cos theta sin theta d theta. Okay, so let V naught theta equal to k sin square theta by 2, just equating k sin square theta upon 2. So now V naught theta equal to k upon 2 1 minus cos theta, because sin square theta upon 2 is 1 minus cos theta upon 2. So now V naught theta will be k upon 2 P naught cos theta minus P1 cos theta. So just putting in f for L equal to 0, we have A naught equal to k upon 4 0 to pi P naught cos theta minus P1 cos theta whole multiplied by P naught cos theta sin theta d theta. So we have k upon 4, just multiply within the bracket, we have 0 to pi P naught cos theta sin theta d theta minus 0 to pi P naught cos theta P1 cos theta sin theta d theta. You can see this second one term here, m not equal to n, that's why this second one is 0. So we got only 2 upon 2L plus 1, which is equal to 2. So A naught will be k upon 2. Next A1, what will be A1? A1 equal to 3 upon 2 or 2r k upon 2 0 to pi P naught cos theta minus P1 cos theta, then P1 cos theta sin theta d theta. Now just multiply within the brackets, we got P naught cos theta P1 cos theta, and another is P1 cos theta P1 cos theta. So here first term is index is not same, so the first term is blows up, sorry 0 not blows up, blows up means infinity. Okay, it is 0. So A1 will be 3k upon 4r, here it is 1, so 2 upon 2 plus 1, so 2 upon 3. Now A1 will be negative k upon 2r. So, but apart all these things, A2, A3, A4 will be all 0. Okay, because for A2 terms, the PL cos theta that we have here will be always 2, 3, 4, which is not 0 or 1 that we have here, P naught cos theta minus P1 cos theta. So always index will be changes, not same, m not will be m number will be equal to n. So always change, that's why this is 0. So we have A naught equal to k upon 2, A1 equal to negative k upon 2r, and all other terms are 0. So V of r theta will be k upon 2 plus k upon 2r into small r cos theta. So by taking k by 2 common, we have 1 plus small r upon r cos theta. This is the required answer to this problem. Okay, A1 is negative k upon 2, right? So this will be plus, sorry, negative. This is right. Okay, so k upon 2 1 minus small r upon r cos theta. This is the required answer to this problem.